Okay, good morning, everybody. Hopefully you can all see me. Hopefully you can see the stream and it's all working as it should be. Welcome. My name's Connor, and again, hopefully you can see, but I'm from a techno camps. I don't know if you've been told a lot about what we'll be doing for the next hour or so, if this is all new to you, or if you have an idea based on the title or have you. But we're going to be looking at and we're going to be talking about fueling the future. The world as we know it is a big, ever-changing sphere of all kinds of weird and wonderful things. And because of this change, because of how it's all working, the need for fuel or some kind of energy source is always changing. And that's what we've been talking about today. How are we potentially going to be doing this kind of thing in the future? How are we going to be relying on the same old methods that we currently use? But before we get to that, I have a little task for everybody. Okay. Now I know I can't see you and I can't hear you, but you do have the option to write in the chat, and I'll be able to see your answers. So what I'd like you to do, just quickly, I'll give about 30 seconds for you to go find something. You don't have to leave the room you're currently in. That's fine. It's ideal if you do stay in the room you're in. It makes the challenge a bit more difficult. But I'd like you to find something in that room that you use on a regular basis. Let's say a regular basis means at least once a day. Okay, something you use once a day in your room that does not run on electricity or batteries. Okay, so have a look around your room. Something that you use at least once a day or more that doesn't require electricity or batteries, and then write what you find in the comments, and I'll give you about 30 seconds or so, or until a couple of answers come through. Okay, if you're still looking for things, if you still want to put them in the chat, that's fine. But I'm going to just move on slightly and read some of the things that people have found. So let me see what we've got. So Claire, what have you said? You got post-it notes and books. Very nice. Jen has a water bottle. Very good. Other people might have different things. Some people, and this would be a very interesting one. Some people might not find something that you use on a regular basis that doesn't require electricity. To take what you just said, Claire, for example, with the books, not everybody reads. Well, first of all, not everybody reads books, but not everybody reads physical books anymore. They have things like Kindles, or they read their books on an app on their tablets and things like that. So books are starting to move, or these stories are starting to move towards a digital setting. Water bottle is a very good one. We all need to drink water, and whether it's through a bottle, a cup, a glass, you can't drink water digitally or virtually. And the idea behind this little task is, first of all, to get you moving around. It's a nice day, have a look around your room, see what you can find. But also, it hopefully makes you realize that most of the things that we use nowadays, and it's not just you, myself included, and most of the people that you will meet, most of the things we use on a regular basis, they are in some way powered by electricity, be it our mobile phones, our tablets, TVs, things like if you are traveling, unless you use a bike, then you travel by car or bus or train or what have you. They're not necessarily powered by electricity, but they do use a different kind of fuel. If you're cooking, depending on what kind of hob or oven you have. That'll be gas or electricity powered. The world around us is very heavily reliant on electricity. And there are several different ways we currently get that electricity. But we might need to change that going forward in, I don't know, 10, 20, 50, 100 years' time. It's very, very likely that we won't be fueling or powering, I should say, these devices in the same way. But before we get onto that, let's talk about how we actually fuel the present. And a big part of it is fossil fuels. Now, hopefully you've heard of fossil fuels. You know, you have at least have a vague idea of what they are. But without them, we would likely not have most of the things that we currently have. Computers, mobile phones, indoor lighting, those kind of things probably wouldn't exist, or they'd look very, very different without fossil fuels. And things like cars and the Industrial Revolution was a big, big driving force not that long ago in terms of civilization anyway. All of these things were driven by fossil fuels. The internet, how many of us use the internet on a daily basis? We're currently using the internet now. That likely wouldn't exist, or it'd look very, very different without fossil fuels. And they have been essential to our development over the last 100 years or so. But they have their own little problems, which we'll get to in just a moment. But as of 2018, and these numbers might have changed, either gone up or down in the last 3 years or so, I'm not 100% sure. But as of 2018, fossil fuels made up 85% of all the energy produced in the world. And they come in 3 different flavors. You either have petrol, coal, or natural gas. Okay, but between those 3, they make up 85% of all the energy produced. The other 15 were from other things, which again, we'll talk about in just a moment. But that's a big, big, big chunk of the energy that we produce coming from fossil fuels. So how do we use them? Does anybody know how we use fossil fuels to produce electricity? And I'll pause there just for a second, give you a chance to think. And if you have any ideas, to pop them in the comment. Claire, I'm sure you're not the only one that couldn't imagine life without the internet, especially nowadays. And in fact, the last 18 months or so would be very, very, very different without the internet. Things like homeschooling, or not homeschooling, virtual learning or virtual teaching, that wouldn't have been possible without the internet. But how do we use fossil fuels to get electricity? Yes, thank you, Claire. In short, we burn them. There's a little bit more to it, but broadly speaking, and since I don't necessarily want people to be typing out the essays in the comments function, and you shouldn't have to. Yeah, broadly speaking, we burn them. It looks a little bit like this. Okay, this is a simplified version of it. It's a diagram. But what we have at the bottom here, we have our fossil fuel. Now, this could be gas, coal, petrol. Doesn't matter, but a fossil fuel. And we put it in the bottom, and we, as you just said, Claire, we burn it. That turns into a fire. That obviously generates heat. And above that, we have this massive tank of water. And what happens to water when it gets too hot? Well, it boils. It turns from a liquid into a gas. And as hopefully you're all aware, gases, they fill up the space that they're in. And so they expand and they rise. And as they expand and they rise, they get forced through this small tube here. The reason why they force it through a small tube is because all of this gas that's trying to fill as much space as possible, going into a very small tube, creates pressure. And as the gas comes through, the pressure goes up and up and up, and that pressure then turns these turbines. And these turbines are connected to a generator. And a generator, to make it as simple as possible, it's a coil of wire around a giant magnet, or the other way around. Okay? Either way, that's all a generator is. And as these turbines turn, this generator turns. So the coil of wire turns around the magnet, or vice versa, and that generates electricity. Now, if you haven't done this in school yet, this is something you will cover a little bit later on. So I'm not going to go into a huge amount of detail of how that generates electricity. All you need to know for now, for what we're going to be talking about, is turbine turns a generator, electricity comes out. That electricity then goes along the wires, the pylons you see around your streets, around the roads, and so on, and that eventually comes out in your house. But there's one extra step. You see, this gas comes in and turns the turbine, but it doesn't continue to be heated. And what happens to a gas once it cools? It condenses, it turns back into a liquid. And it gets recycled, the water goes back into this area here, and then it gets funneled back into the original place where it started. And we have, in theory, a perfect system. What that means is all the water you start with, you never have to add more water. It just keeps going round and round and round. Unfortunately, and this is where fossil fuels, or one of the problems with fossil fuels, is you have to keep adding in fossil fuels at the beginning. Eventually you're going to run out and you need to add more. Once you've burnt a piece of coal, for example, you can't keep burning it. It might burn for a long time, but once it's burnt, it's gone. But this is how you get electricity. And you'd think that's good enough. 85% of the world gets their energy from fossil fuels. It's a relatively simple process. So why bother changing it? Any ideas? Why would we want to change how we generate electricity? So we got two good answers there from Claire. One from Claire, one from Reese. Claire says so it doesn't run out. Yep. And Reese says to save the planet. Jen has also essentially combined those two answers to say something that is more sustainable. All very good points, and all reasons why this probably should be moving away to something different. And we talk in big picture, and when we talk about fossil fuels, it's not all bad. Okay, fossil fuels, yes, there are issues with it, but there are positives to it as well. One of them being how much energy they actually produce. But as you've rightfully said, it's not sustainable. It's harmful for the environment. When you burn coal, you release, or any kind of fossil fuel actually, you release harmful gases into the atmosphere, which is bad for the environment, as well as waste and so on. It's not renewable, which means once you've burnt it, once you've used it, you can't use it again, which means that you only have a finite amount. Okay? You only have so much of it. Once it's gone, it's gone. And again, that comes back to the sustainable approach as well. When you can't keep using something if it's going to eventually disappear, you need an escape route and something different. But like I said, there are pros to it as well. It's not all bad. Yes, it is getting to the point where it probably is doing more harm than it is doing good. But without it, like I said, we wouldn't have all the things that we currently have. As you just said, you couldn't live without the internet. We probably wouldn't have the internet without fossil fuels. It is, compared to other means of producing energy, it's relatively easy to do. You have a fossil fuel, let's say it's a piece of coal, for example, you light it on fire, and you have energy. There you go. And the infrastructure is in place. This is an important one because we've been using fossil fuels for so long. All of the power plants, or most of the power plants around the country, or indeed around the world, are already set up to generate electricity using them. If we were going to move to something else, then those power plants would have to change, or these new devices would have to be built. So it's already there to use fossil fuels. It would take a big effort to change to something else. But that's not to say we shouldn't be changing. And in fact, there are already alternative fuel sources. Can anybody give me any examples of alternative fuel sources? Because we've got Claire saying wind, Jen and Reese are both saying solar. Yep, those are probably two of the most famous ones, or most well-known ones. But we do have lots of different renewable energies. There are other alternatives, but I'm going to focus on renewable sources in particular here. But we've got wind, as you said. Tidal is another big one. Biomass, which is taking things like food waste and wood and that kind of stuff and burning those. Solar, like you've said, is another popular one. But even all of these together only make up the last 15%. And actually saying that, the renewable energy sources only make up about 4%. Okay? Nuclear power, which is a different kind of energy source to fossil fuels and renewable sources, that makes up just shy of 5%. Hydroelectric is almost 7%, and then renewables is less than 4%. Okay? But renewables is the one that people focus on the most. But that makes up very, very little of how much energy we produce. Again, these numbers are from 2018, so that might have changed by now in the last 3 years, but going off 2018 numbers anyway. So why do you think that is? Why is it if we have solar power available to us, we have wind power, we have tidal power, and all these other renewable sources where you can just keep using them over and over and over again, why do you think we don't use more of them? Why are we still so heavily reliant on fossil fuels instead of moving towards these renewable energies? Well, the answer is very similar to what we talked about with fossil fuels, in the sense that fossil fuels have pros and they have cons, and they have good points and bad points. It's the same with these renewable sources of energy. They have good points and they have bad points. One of the big things they have going for them is that they're renewable. Most of them, if not all of them, are environmentally friendly. But they do have lots of big downsides, which people tend not to talk about. For example, wind power, it only generates electricity when it's windy. You can have a massive wind turbine, and when it's windy, it can generate loads and loads of electricity. When it's not windy, it does nothing. Okay? So that's only, even though it's good every time it's windy, it will generate electricity for you. When it's not windy, it doesn't do anything. So that's not great. Tidal power, where you have to build these massive units around a coast. And when the tide comes in and goes out, it turns these massive generators. But in order to make things safe, sturdy enough to take all that water, or lay all the cables and so on. It's expensive. Okay, so we're talking about the infrastructure. When I said about the infrastructure with fossil fuels, they're already there. The power plants are already there. We just have to keep putting in the fossil fuels. If we want to use tidal power, we need to build different power plants, and that's going to be expensive. Biomass, yes, it's renewable, but you're still having to burn things, and then you're still releasing bad chemicals into the air. You're still releasing lots of carbon dioxide into the atmosphere. That's bad for the environment. So it's renewable, but you're still harming the environment. Solar power is relatively inefficient, which means that it doesn't matter if you have hours and hours of sunlight, you're not going to get hours and hours of electricity out. You're only going to get a little bit. And if we're being perfectly honest, lots of these downsides, they overlap as well. So wind power, not only does it only generate electricity when it's windy, but it also doesn't generate or doesn't turn all of that wind energy or that kinetic energy into electricity. Okay, so it's not very efficient in the same way that solar power isn't very efficient. It is more efficient than solar power, but again, you have these overlapping problems. So people have tended to just stick with fossil fuels because it's the easier option. But the easy option doesn't necessarily mean it's the best option, especially now as things in the news about climate change and so on are becoming more and more relevant. It's now time to start thinking about how are we going to keep the lifestyle that we have all become accustomed to? How are we going to continue to provide the electricity for the whole world without using fossil fuels? How are we going to fuel the future? And that's a problem the world is trying to solve. Everybody across the world is trying to solve these problems. And they've yet to find a solution. But I have a little idea. Now, I'm not going to claim to be able to solve that problem myself, but this tip or this technique that I'm about to talk about could be useful for you in things like school or other areas of life. Okay. But before that, let's try something slightly different. But trust me, there's a method to my madness. Okay. I'm going to show you some pictures. And these are pictures that have been zoomed in. And I want you to have a look at them and think about what they are. And then write down in the comments what you think it is. And then we'll go over the answers at the end. Okay? I think if I remember off the top of my head, there's 6 pictures to look at. 5 or 6 anyway. So here's the first one. Look at it. Think about what you think it might be. And then type it into the comments. Okay? You'll have about 20 to 30 seconds to look at each picture. Okay, next one. I've just seen your comments about not using in renewable energies, and you make some very good points. Making change takes effort. It relies on the environment, which isn't always consistent. So that's the wind power we're talking about. Lack of technology. So there's ideas that we don't have the ability to implement yet. So very good ideas there. Well done. So far we've got a turbine for the first one, toothbrush for this particular one. Okay, here's the next one. So this one, if it helps anybody, this is a food. And some of you might have eaten it. You You might have come across it in the supermarket, in the fruit and veg aisle. Reese is on the right track, but it isn't an egg. Inside a solar panel, it's a nice idea, and it does look similar to a solar panel, but it's more mundane, more boring than a solar panel. Okay, move to the next one. So this next one, once you can see it, this will give you another clue. This one smells really nice, or at least some people think it smells very, very nice. Again, you're on the right track, Reese. Not quite chocolate, but you are on the right track. Claire, you're closer than Reese with coffee, but you're not quite there. But you are on the right. Again, you're on the very, very right. You're very close. It does begin with a C. Okay, let's move to the next one. This one might be one of the hardest ones, but I'd imagine you've all seen this before. And you might have all used this before, but this is probably the hardest one. Picture of Mars. It's a lot smaller than Mars. A lot smaller. Reese is on the right track. It is a type of wood. Okay, move on. And this is the last one. And then we'll go through the answers. Claire says it's candy floss. Reese thinks it's a pink sponge. Okay, let's see what these things were. So this first one, this was one of the more difficult ones. But you'll probably kick yourself when you see what it is. These are book pages. If you imagine you're in a dark room, you open up a book and you're looking at the pages edge on. And that's what this one was. This next one, Reese was close when he said toothbrush. It is a type of brush, but this is the bristles of a paintbrush or a makeup brush, that kind of thing. But I'll give it to Reese because he said they had brush in the name, so well done. This one, I think Jen, you got this one. I think you were the one that said it was a melon. If I'm right, if I check. Yeah, Jen, you said this was a melon. Well done. This is a cantaloupe melon. So next time you go through the fruit and veg aisle, you'll see the pale yellow shape, and they've got these weird patterns on the skin. So well done for that one, Jen. This one, nobody got this one, but like I said, you were close with chocolate and coffee. This is cinnamon. cinnamon. If you've never seen cinnamon out of not as a powder, it comes in sticks. They look very similar to little wood pieces of wood, but cinnamon, this is what it looks like, and it does smell very nice. At least some people think it smells nice. This was, like I said, the hardest one. Reese, you were right. There was a type of wood, but this is cork. Okay, so cork you might find in the top of a bottle or on message boards, that kind of thing. That's the type of wood this was. And in the last one, it was a 50-50 between a lot of you, or between you. It was either candy floss or a sponge. And this one was a sponge. Okay, it's the rough side of a sponge. Okay, so well done with those. They weren't easy pictures, but like I said, there is a method to my madness, and none of these pictures have anything to do with producing energy or fossil fuels or renewable energies. That's not the idea. All those pictures had in common were that they were zoomed in. Some of them were also foods, but that was just a coincidence. And what we're trying to show here is that if you look at something differently, it can appear like a completely different thing. If I showed you a picture of a book or a sponge or a cork, you'd be able to tell me straight away what that was. But even though these are all common items and most people would be familiar with, as soon as you zoom in on it, look at it differently, it starts to appear like a completely different thing. It's a completely different problem. And that's what I think people should be doing about this fueling the future problem. Everybody's trying to figure out how we produce electricity. How can we do this without using fossil fuels? And most of these processes that we've talked about, the fossil fuels, nuclear power, wind power, hydroelectric, and so on, they all involve turning a turbine. You have some means of turning a turbine. This turbine turns, which turns a generator. And they all do it slightly differently, but that's what they all do. The wind blows the blades, that turns a generator. Nuclear and fossil fuels, they boil water, which creates steam, which generates electricity. Hydroelectric uses water to do that, turns a turbine. The only one that's different is solar power. Solar power does not require turbines or movement of any kind. Solar power uses specifically designed bits of plastic that absorbs the energy from the sun, and it makes electrons move. Now, in case you haven't covered this in school just yet, everything in the world is made of atoms, and atoms themselves are made of a nucleus, and they're made of an electron, or a certain number of electrons. And by definition, if you can make these little electrons move around a circuit from point A to point B, then you have electricity. And that's all electricity is. And solar power uses the energy from the sun to make the electrons in this material, in this plastic material, move from one place to another. And that generates electricity. No moving parts, no fancy steam power or anything like that. It is just using the energy from the sun. And maybe this is what people should be focusing on. Not how do we turn a turbine, but how can we use solar power differently? Because if we think about it, the sun has been around for nearly 5 billion years, and it's going to be around for somewhere in the realm of 5 billion more. That's longer than any of us will ever be around. And despite looking at it, the sun is not a big ball of fire. It looks like a big ball of fire, but it's not. It's a giant nuclear reaction, but it's different to the nuclear reactions that we use here on Earth. We use something called nuclear fission, but this is nuclear fusion. And I'll cover what those two are in a little bit. That's not important for what we're talking about at the moment. I want to talk about what the sun is made of. Yes, the energy generated by the sun, it comes from nuclear power, but it also comes from something called hydrogen, which, again, in case you haven't heard of it before, is the lightest element in the universe. There's more hydrogen in the universe than just about anything else as well. It's all around us. So if the sun can use hydrogen to power itself for nearly 10 billion years from start to finish, and hydrogen is all around us, maybe we can use hydrogen to produce electricity, to produce power in a similar way. Now, we can't do exactly the same as what the sun does. We don't have the technology for that just yet. But that doesn't mean we can't start looking at hydrogen to do it, to produce electricity in a different way. Hydrogen power is something that a lot of companies, a lot of energy companies are looking at. It's something that could very much start replacing fossil fuels. It could become the way that we fuel the future. And it's interesting to think, when I say hydrogen is all around us, it is. 70% or so of planet Earth is covered in hydrogen. The only problem is hydrogen is very, very reactive, which means that it reacts very quickly with other things. And when you get hydrogen and oxygen together in the right mix, they make water. So we have loads of hydrogen here on Earth. Like I said, about 70% of planet Earth is covered in water. And 2/3 of that water is hydrogen. So if we could separate that from water, then we would have this huge amount of fuel that we could use to potentially power planet Earth in some way. But before we get to how we could use hydrogen, let's think about how we're going to get that hydrogen out of the water. And it's actually a really relatively simple process. It's one that you could do at home. We'll cover that in just a second. But it's called electrolysis. And what you have is you have two pieces of metal, two pieces of metal attached to a battery or a power source. But let's say it's a battery for now. And we have batteries that have a positive end and a negative end. So you connect that battery to these two pieces of metal, and one of those pieces of metal becomes positively charged, and that we call that the anode, and one of them becomes negatively charged. We call that the cathode. And then you put these two pieces of metal that are attached to a battery into water. And inside that water, you'll put a little bit of salt or something similar to salt, okay, just to kickstart the reaction. But as soon as you put them both in the water, they'll start to react. They'll react with the water. And what you'll see is, because of the current going through the battery, as the two pieces of metal go in, the current travels through the liquid, through the water, and it splits the hydrogen and oxygen into separate components. You have hydrogen goes to one, hydrogen will go to the cathode, and oxygen will go to the anode. Okay? Because hydrogen is positively charged, oxygen is negatively charged, and opposites attract each other. Like magnets, we bring opposite sides of a magnet together, they stick. It's the same with positive and negative charges in atoms. And what I want to show you now, just quickly, I'm going to show you what this would look like if you were to do it yourself. And as I'm showing you, I will talk you through how you might do it yourself as well. Okay, so hopefully you can see this video playing. Don't worry about the sound. I'm going to talk over it. Okay, so let's press play. What we have at the moment, actually, let me stop it there. Stop. What we have is a plastic cup and two drawing pins, and then a 9-volt battery. Okay, and you'll see now if I press play. So there's the two drawing pins in the little plastic cup, and the little pointy ends stick out. So these are going to be our cathode and anode. And you've got the 9-volt battery with the two contacts sticking up. Now you could do this, if I pause that there a second, if you wanted to, you could do this yourself at home. It doesn't take a lot to find the things you need. In fact, most of you probably have these components lying around your homes anyway. Now, at the moment, there's no water in it, so nothing's happening. But this time, so you see the water in there now. Don't worry too much about the two tubes. But as soon as you bring the cup with the two drawing pins onto the battery, you can see bubbles starting to form. Okay, so the one on the right-hand side has a lot more bubbles than the one on the left-hand side. And hopefully you can see that. Hopefully that's clear for you to see in the video. But yeah, the one on the right-hand side has more bubbles than the one on the left-hand side. But this is, if I stop it there, this is electrolysis on a very, very small scale. Okay, you're not going to power the city with this little demonstration. You're not going to power your house with this demonstration, but it is a demonstration of how this process works. Now, just as I'm swapping back to my presentation, have a think. Why does the one on the right-hand side of the video have more bubbles than the one on the left-hand side of the video? And I'm going to swap back. So does anybody have any ideas why the one on the left has more bubbles than the one on the right? What could you explain that a little bit more, Daisy? Where you said both left charges are the same? It is something to do with the positive and negative charges. Thank you, Reese. Very good, Jen. Yes. So for those of you not 100% up on their chemistry, water, or another name for water, is H2O, which means there are two hydrogens for every one oxygen. And when you split them off, because there's twice as much hydrogen as there is oxygen, you will get more hydrogen than you will oxygen. You'll get double the amount of hydrogen to oxygen. So you'll see twice as many hydrogen bubbles as you would oxygen bubbles. But you are right when you said about the positive negative charges, because all the hydrogens are positively charged. There's more of those going to the negative side. So that's why you get double there. And you're right in saying that they're both on the left-hand side have the same charge, as all the hydrogens have the same charge. So well done with that one as well, Daisy. So very good answers there, everybody. How does this help us then? Okay, if we can perform electrolysis and we can split hydrogen and water, now we have hydrogen. Great. What are we going to do with it? What's the point of having all of this hydrogen? Well, long term would be to do exactly the same as what the sun does, but we can't do that yet. So what can we do with it in the meantime? Anyway, there we go. We can produce, or we can make, what's called a hydrogen fuel cell. Remember I said about solar power, how it produces electricity by making electrons move. And if you can make electrons move from A to B, then you have electricity. Well, hydrogen atoms, they have one electron. Every hydrogen atom has one electron. Now, if you can make all of those electrons from all of those hydrogen atoms move, then not only do you have electricity, you have a lot of electricity. And if you have lots of hydrogen, you have lots of electrons. The trick there is then, how do we get the electrons within hydrogen to move around? And what do we do with them once we've moved? Or once we've moved them? And then how can we use this to replace fossil fuels. And that's where the hydrogen fuel cell comes in. Hopefully you can see this diagram. It should be animated for you when you're looking at it as well. But this is what a hydrogen fuel cell looks like. On the left-hand side over here, we have hydrogen coming in. On the right-hand side, we have oxygen. We'll get to the oxygen in a minute. Okay. The hydrogen comes in. So we've used electrolysis. We've split the hydrogen out of the water, and now we've funneled that hydrogen into our fuel cell. It comes in, and it gets drawn towards this green section in the middle. Now, don't worry too much about what this green section is. All you need to know about this green section is it doesn't let electrons move through it. Okay, that's the only important part about it. What happens is the hydrogen comes in and it gets split. The nucleus, the middle of the hydrogen atom, just goes through that green bit as if it wasn't there. But the electron, that can't go through that green bit, so it has to go somewhere else. So these hydrogen fuel cells, they funnel it through wires up here, and these wires, just like any other wire, just like any other circuit, are connected to, in this case, is a bulb which lights up, but it doesn't have to be a bulb. It could be a motor. It could be, I don't know, it could be your electric hob, for example, so you can cook things. Just has to be part of the circuit. The electron goes through, it powers the circuit, and because circuits don't work unless they're connected, it has to come out the other end. When it comes out the other end, it ends up in this right-hand side of the battery, of the fuel cell. On the right-hand side, it recombines with the nucleus, so it comes back together, and hydrogen comes back as a whole atom. But also, you pump in oxygen. Now, this oxygen comes from the air around us, so you don't have to specifically have an oxygen pump. It's just oxygen is around us. So when the electron comes back to the other side and it recombines with the hydrogen nucleus, you get hydrogen on its own, and then the oxygen comes in, and hydrogen and oxygen combine together to produce water, and the water then just gets funneled out as vapor, as a mist. You also get a little bit of heat as a byproduct of the reaction, but that's fine. We get heat from batteries anyway. Or when we generate electricity in other ways, we get heat anyway. And we could even use that heat for other things, so it doesn't go to waste. But what we have now is, in theory, a completely clean form of producing electricity. And what I mean by clean, it's also renewable. We'll get to that in a second. What I mean by clean is you don't get any waste. You get water vapor, sure, but water vapor isn't harmful for the environment. It's not bad for us. It's just water. It's not like when you burn fossil fuels and carbon dioxide goes into the air. It's not like when you have nuclear materials that are radioactive for hundreds of years. It's nothing like that. This is a clean form of energy. And it's also already being used. It's still sort of developmental, which means that it's only used on a big scale at the moment, but it is being used. It's no longer a future idea. It's currently being used to power some cars. We call those hydrogen cars. And these hydrogen cars have, instead of fuel tanks where you put petrol or diesel in, they have a hydrogen battery, hydrogen fuel cell in them. And you fill them up with hydrogen. That hydrogen then goes into the fuel cell, and what we just talked about happens. And instead of having a bulb that lights up, the circuit is attached to a motor. That motor then turns, and it turns the wheels, and the car drives. So we could start now looking at what else can we replace with hydrogen fuel cells. We've already started to replace fuel tanks and petrol and diesel cars with hydrogen fuel cells. What else could we replace? Could we replace the pylons, or rather not the pylons, sorry, could we replace the fossil fuel burning section of power plants, replace those with hydrogen fuel cells, and then have that electricity travel through the wires into our homes? And that way, all of our electronic devices at home are powered by hydrogen instead of powered by Fossil fuels. These things, though, these are all speculations. These things aren't actually in the work at the moment. Hydrogen cars are. You can buy hydrogen cars from certain companies, but anything other than hydrogen cars, that's still being developed. So these are still future ideas. But because the technology is there, the future might not be as far away as we think it is. And long term, how does this help us? Well, electrolysis is a relatively simple way of producing hydrogen. It doesn't take a lot of energy to do itself, and you could use solar power to produce to do electrolysis to produce the hydrogen. And in fact, there's a company in Wales, in Bridgend, so not too far away, that currently do this. They have this massive building which is covered in solar panels. Those solar panels are connected to a big machine which does electrolysis, like we just showed you. That splits hydrogen and oxygen into separate atoms. They then collect that hydrogen, and they have an agreement with the local fire department, who have a couple of these hydrogen cars, that they produce the hydrogen, and then the fire department bring the hydrogen cars around when they need refueling, and they refuel the cars with hydrogen. So it's already happening. It's not happening in lots of different places, but it is already happening, and it's happening on our doorstep. But that means we have access to a lot of hydrogen, and it's a renewable source of hydrogen as well, because as soon as that hydrogen recombines with oxygen, it produces water. We can collect that water, and we can do it again. So hydrogen doesn't get used up. It doesn't get used up in the process. It can be reused. We can then take these batteries, these fuel cells, and put them in cars instead of petrol and diesel cars. And maybe in the next few years, you'll see more of them on the roads. And maybe in a few years after that, you'll stop seeing petrol and diesel cars. They'll replace them altogether. And with more research and more development, who knows what else we can start to power using these hydrogen fuel cells. It could be that we replace power plants altogether with them. Who knows what else we can do with them. But it's only a matter of time. As long as people keep researching and developing this technology, it's only a matter of time before it gets smaller and more efficient and better. If you think about computers, we're all using a computer today. You might be using a laptop or a desktop, doesn't really matter. Either way, they're quite small. Computers, about 60 years ago or so, were, or maybe a bit longer, maybe about 70 years ago, were the size of whole rooms. But because people kept working on them and developing them, they got smaller, they got better, they got faster. And the same can be true of this hydrogen technology. And who knows, if they keep developing it, then we might be able to crack hydrogen fusion. And this would be the end goal. This would be how we produce energy cleanly for the entire world. And it's how the sun produces electricity. At the moment, when we use nuclear power, we split big, heavy atoms. Big, heavy atoms, like plutonium, for example, they get split. They get split into two different atoms. And when they split, they give off energy. And this happens over and over and over again in what's called a chain reaction. So this gives off lots of energy, but the atoms that they get split into, they're radioactive, they're dangerous. So nuclear power is good for some reasons, but it's bad for others, in the same way that fossil fuels are. Hydrogen fusion, however, is the opposite. You take small atoms, you take hydrogen atoms specifically, and you smash them together. And when you smash them together, they don't split, they stick to each other, and they produce helium. And when they stick to each other, they produce helium, and they also produce energy. And if you could do this a lot, to do this enough times, you get a chain reaction going, then you produce helium, which is inert, which means it doesn't react with anything, so it's not dangerous, and you get energy. And this is how the sun does it. It's how the sun produces all of its energy and has been doing it for 4 and a bit billion years. If we could do this, we could solve the whole world's energy crisis. But at the moment, We can't make this self-sustaining. And what self-sustaining means is that we can't make it generate enough energy so that it keeps itself going. We have to keep putting in energy to keep it working, which means we lose energy in the long run. But this is being worked on, and hopefully in the future, not too distant future either, this could be a real solution to our problems. So, where are we at? Well, we're at a point where we have ideas, we have potential uses or options to replace fossil fuels and even replace other renewable sources of energy, but they're slow, they're in development, they're in the early days. But there is light at the end of the tunnel. We can produce hydrogen fuel cells. We could in the future produce hydrogen fusion. And with these things working together with wind power, with other solar power and tidal power and so on and so forth, you might see the end of fossil fuels in the near future. And this could be in one way that we fuel the future. But who knows? Who knows what it brings? This is just a speculation, an idea. Could be something totally different. But I don't have all the answers, unfortunately, and we are just about out of time. So thank you very much for listening. Hopefully you've enjoyed. Hopefully you've learned something. And hopefully we'll get a chance to do something similar again in the future. So thank you very much, everybody. And we'll see you again at some point, I'm sure.